Voit, will you tell us about the CGM format precipitation?
Thank you. Well, first, I'd like to thank the organizers. This is my first visit to India. I've been interested in coming to India for a very long time. I'm enjoying it tremendously, so thank you for that. I also thank Jess for a terrific introduction to the Certain Galactic Medium, which takes a little of the burden off me to explain everything about it. Although the Certain Galactic Medium, from my perspective, is going to be somewhat different from what you heard from her. Because the way I'm coming at the subject is from the most massive galaxy in the universe. This is the central galaxy, the Perseus cluster, NGC 1225. I've been studying the multi-phase medium around brightest cluster galaxies for almost 30 years. So I've been working on the Certain Galactic Medium for 3 decades. I just didn't know what it was called until recently. Starting from this point, one of the reasons that these systems are so interesting to study is because you can get a whole lot of the information about what's going on in the circumgalactic medium from multi-wavelength studies. In a way, we can see a lot of the moving parts in an object like this, and we have to infer the kinds of things we have to infer around galaxies that are more like the Milky Way. For example, here you can see the central galaxy. You can see star formation happening at some large distance from the central galaxy. You can see H alpha nebulosity going out to quite large distances from the central galaxy. With an X-ray image, you can see the ambient circumgalactic medium. Usually it's called the intercluster medium, but for this conference, it's going to be the circumgalactic medium if it's within 100 kiloparsecs. The red is radio emission, showing there are bubbles being inflated. You can see in the X-ray there's cavities where those bubbles are being inflated. So you're seeing the active galactic nucleus interact with the circumgalactic medium. You're also seeing the rich multi-phase structure of the circumgalactic medium. And what I'm hoping is I'm going to talk about lessons learned from systems like this, and then try to move downward in mass to see how far they can be extended. There's a question there.
What is the scale here?
10 kiloparsecs is about like this. Okay. Now, I also want to show, since this is a conference about bubbles, I want to show what happens when people take the X-ray image and do unsharp masking to bring out the details. So here is the circumgalactic medium around the Perseus cluster, and you can see the bubbles that are obviously filled with radioplasma, but also a whole lot of other rims that may be bubbles that were previously blown. And so around brightest cluster galaxies, there's a long history of blowing bubbles. And the disturbances that are created by that have implications for why this whole thing is multi-phase. So I'll step back and start with the discovery. I'm going to be talking about an even older paper than the one Jess pointed out. I know it's a paper that Jess knows about because they referenced it, like reference number 1 in their review article. It's a paper by Lyman Spitzer. How many of you were alive in 1956? Nobody's up. Very good. Born in 1956. Were you born before or after March 24th? Okay. So this is a paper by Lyman Spitzer. And when I gave a colloquium at Princeton back in September, Ed Jenkins told me that what Spitzer and Schwarzschild used to do would be to travel to Carnegie observatories once a year. They get on the train, they go out there, and talk to the observers about what they were seeing. And so on one of those trips, Lyman Spitzer learned from Guido Wundt that there were absorption lines from low ionization gas along the line of Satan's elevator above the galactic plane. And he started thinking about this. Those observations weren't published until 5 years after this paper. But this is the discovery of the circumgalactic medium. And from those lines, he inferred that there would be an ambient medium. So we argued just an hour ago or less about whether the Milky Way has a hot ambient medium. Spitzer simply assumed that there was to confine these clouds, assuming also that the temperature of that medium would be like the virial temperature, he was able to calculate what its cooling rate would be and calculate the rate of cooling at that temperature would dissipate the assumed thermal energy in about 10 to the 9 years. Since he was a plasma physicist as well as an astrophysicist, he knew free cooling wasn't enough. You also had to account for the line emission from things like iron. And here he estimated the cooling time at 10 kiloparsecs from the center of the Milky Way was about 10 to the 9 years. And that posed an issue, right? This medium might be condensing. There's time enough for it to cool. He said condensation of cool matter from the corona may perhaps account for the formation of new spiral arms as the old ones dissipate. And he pointed out that maybe there was thermal instability of this matter in the galactic corona. 1956. We know a little more about the corona today, but this is already, I think of this now as the first cooling flow problem. People talk about cooling flows around X-ray clusters since the 70s, but even in 1956, Lyman Spitzer is thinking about radiative cooling around the Milky Way and wondering how that stuff stays in equilibrium. Here's a diagram showing how I like to think about the circumgalactic medium. It is simply a phase diagram, but instead of the usual axes of temperature and density, these axes are pressure and entropy, and temperature and density are on these diagonal lines. So if you have a monatomic ideal gas, the pressure is proportional to some constant times the density to the 5/3 power. And if you know any two of these variables, temperature and density or entropy and pressure, you can calculate how long it takes the gas to radiate away its thermal energy in cooling time. And this constant proportionality is related to what adiabat the gas is on. It's directly related to specific entropy. If you take the logarithm of it, you get the classical thermodynamic entropy, but X-ray astronomers tend to call this the entropy. If you divide both sides by density, if you divide both sides by density 5/3, you find that this K is proportional to temperature divided by density to 2/3 power, and so K in the X-ray literature is defined like this. And it is a very useful quantity to track when you're trying to understand whether the gas is gaining or losing heat energy. So also on this plot are lines of cooling time, constant cooling time, and you can see that the temperatures are characteristic of the circumgalactic medium, the ambient circumgalactic medium. The lowest order, the cooling time, it has a one-to-one relationship with the entropy. Now, when you orient the plot like this, the things that happen due to hydrodynamics tend to be moving you around in the horizontal direction on the plot. The things having to do with thermodynamics tend to be moving you vertically. So if you are heating or adding heat energy or removing heat energy, you're going to go up and down in entropy, perhaps at constant pressure. If you are just compressing or letting gas expand, you're going to be moving around in this direction. So, adiabatic cooling, if you just let gas expand, it's going down in temperature, it's going down in density, but its cooling time, if you're in this temperature range, is staying about the same. Okay? The changes in temperature and density cancel. Or if you compress it, it's going off in the other direction. And so, this is a statement I made a minute ago. If you're in this temperature range, that's the typical virial temperatures of galactic halos, the temperature, the cooling time is actually insensitive to the pressure. It really depends on entropy. What does that mean? Well, if you have shock heating, you're going to go in this direction of the plot. You're going to both higher pressure and higher density, and the cooling time is going up. So if in this temperature range, shocks don't induce cooling. They make it harder to cool. If you have a homogeneous cooling flow, you'll tend to go down in this direction. The temperature of the gas doesn't change because you're in a gravitational potential well, but it's losing heat energy. So people sometimes look at temperature to try to figure out when the gas is being heated and cooled. That's not the right approach. Another example is star formation. You have a blob of gas, it's radiating energy away, and it's warming up to the center because the gravitational potential is compressing it. Okay? So if you want to know whether the circumgalactic medium, circumgalactic gas, is gaining heat energy or losing heat energy, this is the quantity that you want to track. And so, Lyman Spitzer, since he was able to estimate a pressure, he could put a plot, he could put a dot here on this plot, and found the cooling time of the Milky Way at the distance of the sun from the center is about 10 to the 9 years. And the takeaway from this section, I'll leave it to Lyman, is, quote, the problem with the origin of such a corona reduces permanently the problem of heating. How does it sustain in that state? So now, what was called the corona for a while, we now call the CGM. And I don't have to spend very long on these slides, it just gave the introduction, but if you are, I'm gonna give a shout out to the CGM as being really, really important. This room doesn't need it. But if you're setting out to write a textbook, 25 years ago, would put in a diagram talking about these being the main parts of the galaxy, our galaxy. But around about 20 years ago, people recognized that really the central black hole is an essential component. Its mass is tied to the bulge mass of stars, and it seems now that the central black hole's evolution is intimately related to the evolution of the galaxy as a whole. I think the trend in the 2010s is to recognize the circumgalactic medium as just as an important part of the galaxy. The analogy I sometimes think of is if you want to understand an egg, you can't just study the yolk. The other part, the white part around it, is just as important and really nourishes what goes on at the very center. We've already heard most of the galaxy's baryons and metals around here, and there has to be transfer of matter back and forth from the galaxy up to the circumgalactic medium. When we move up to massive elliptical galaxies, it's been known for a long time. They have radio jets, and from the morphology of those radio jets, you can infer that there's an interaction. Jets coming out from the central galaxy, and they're interacting with something around it, even if you can't see it. But if you have an X-ray telescope, you can see it. And what we've recognized over the last 10, 15 years, using Chandra and XMM observations, is this is a finely tuned system. The black hole is putting out just enough energy to keep the circumgalactic medium around the galaxy from condensing and cooling and feeding the galaxy with star-forming gas. The puzzle is, how does this engine that's down at parsec or smaller scales know how much energy to put out in this environment that's tens of kiloparsecs in size? This is a tuned system, and yet the size scales are hugely mismatched. Okay? But circumstantially, when you measure the energy output and the cooling, they're about the same. Going back to this plane, I want to show you a few galaxies. This is the Milky Way. That is actually not the Milky Way, but it looks close enough to the Milky Way. Okay. So putting the Milky Way's structure in this phase diagram, this line comes from the X-ray analysis of Miller and Bregman, where they are looking at oxygen 7 and oxygen 8 lines along many different lines of sight from Chandra, and modeling that with a smooth ambient medium. So, to answer the question we posed half an hour ago, you can see the Milky Way's hot ambient medium in X-rays. Okay, there's a hot ambient medium there. Also, you can see that its density and temperature are about what Simon Spitzer inferred in 1956. Probably be thrilled to find out that he was right. Okay. Now, I'm going to step up. This is NGC 4472, massive elliptical galaxy. You can use an X-ray telescope to measure what the run is of density and temperature. The gas is close to isothermal. That's why these things are tracking the temperature slope. And the cooling time gets very short near the center. Down at tenths of a kiloparsec, the cooling time is 10 to 7 years. And yet, there's no star formation in this galaxy. It's not cooling and forming stars. The galaxy's stars are putting out, the old stellar population is putting out all the mass, but it's not collecting in the galaxy and forming stars. In order to stay in this state, you have to have a very finely tuned feedback mechanism. Curiously also, you can see, even though the galaxy is quite a bit more massive than the Milky Way, looks quite a bit different, the pressure is 2 orders of magnitude higher, the cooling time and entropy structure is not much different. Let's step up further. Here's M87, a central cluster galaxy. Again, cooling times get very short near the center. another almost a factor of 3 up in pressure. But the cooling time at 10 kiloparsecs is about a gig a year. Let's go up some more. NZ 1275, the Perseus cluster. Again, the cooling time at 10 kiloparsecs is of order a gig a year, but less. And so, is this a coincidence? I don't think it is. I think this is telling us something very fundamental about how the circumgalactic media of galaxies, the Milky Way, and more massive is regulated. Okay. Another thing that's curious, and Jess mentioned this, but maybe not about massive galaxies, people who have done large-scale absorption line studies with Sloan, looking at magnesium 2 lines, have found if you compare the offset, the velocity offset between the galaxy and the cloud, that the velocity dispersion of those clouds is significantly less than what you'd expect from the halo mass. It's about half. Okay, and that is strongly suggestive that there is an ambient medium that is close to hydrostatic. There may be some turbulence, but it's a turbulent velocity that's quite a bit less than the sound speed of the medium. Okay, and so these circumgalactic media around massive galaxies, to lowest order, are hydrostatic. They are not violently turbulent. We don't see dramatic, for most of the mass here, it's probably not going out in or out dramatically. There's probably an ambient medium. And that ambient medium is finely balanced. And I will now talk about one of my pet peeves. Okay, I have been present in a lot of talks where people talk about quenching of galaxies, star formation galaxies, as an event. Something happens, the AGN rears up and blows out all the molecular gas, and then you're done. Okay. But the plot I showed a minute ago shows the cooling times of the ambient medium are still very short. You have to continually maintain that state. So simply blowing all the molecular gas out of the galaxy doesn't stop the star formation over long periods of time. The key to quenching is understanding how the galaxy can maintain that state. It's a long-term state of balance that has to be understood. Right. Multi-phase central cluster galaxies. For those of you who haven't been studying for 30 years, I thought I'd introduce you to one of my friends. It is a central galaxy that is called 2597. And here I'm depending a lot on the work of Grant Tremblay and his collaborators, of which sometimes have one. And so this is a composite X-ray optical H-alpha image of the central galaxy in Bell 2597. The blue is the X-ray, and here you can see some bubbles. And before I go and talk about the other stuff, I wanted to show a picture from a paper in preparation. This is showing even deeper X-ray data that has been processed in the same way as that title image before. It's unsharp mask, so you can see the fine features. And here's on a 45 kiloparsec scale, bubbles, 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 bubbles. There are areas pointing to them here, okay? And so, again, NC 1275 isn't unusual. If you look hard enough at these things, you find they blow lots of bubbles. You also find in these contours, these are H-alpha contours in green. The purple or deep blue contours are carbon monoxide CO emission. You find that there are distinct spatial relationships between the bubbles and the multi-phase gas that's in these galaxies. Okay, and we'll dig down on that. So here's, so you can see the optical emission from the galaxy here in yellow. The red is H-alpha emission. That's a UV image showing Lyman alpha emission. And you can see, I'll back up, it's generally extended in the directions of where the bubbles are, suggesting uplift. We'll zoom in. Okay, so here's the Lyman alpha contours. These are the radio jets of the currently young radioplasma. And they are oriented along the same direction as Lyman alpha is extended. Superimpose some more. Here are the radio contours. The blue here now is far UV light. That's young stars. The star formation happening, and the star formation tends to track the edges of the radio plasma. So the AGN interaction in this case is correlated with star formation, where the star formation is happening in this galaxy that, a lot of people think ellipticals are red and dead. Well, the brightest cluster galaxies that can be quite significant star formations connected with the activity. Zoom in some more. This is an observation of CO emission. Here's some of the CO emission again, aligned along the radio jets, suggesting I think this is uplift here going on. But if you then concentrate right on the nucleus and use it as a backlight and ask, what do you see there? You see, well, a CO emission line and then 3 absorption lines. Okay? They're all redshifted. So there are 3 molecular clouds that are falling into this black hole at roughly the virial speed of the galaxy. Okay? And taken together, it looks like there's both outflow correlated with the radio bubbles and inflow of molecular gas right into the black hole at the center. Okay, so this is one of these things on many different scales. So the solar conductive medium knows about the AGN and vice versa. And while all that looks very complex, one of my central arguments in the talk is going to be there's a remarkably simple principle that helps kind of all that to gel. And to understand it, yeah.
So the molecular clouds falling the black hole, how does this velocity, infall velocity, compare with the gravitational redshift close to the black hole?
Okay. It is thought, when you can make statistical arguments to guess at how far the clouds are. They're still about 100 parsecs, and so you don't quite expect the black hole to be taking over. And that estimate comes from looking at the extent of the molecular emission, trying to estimate how many clouds there are, what's the likelihood that one would be along the line of sight, et cetera. So they should not be so close that they are being strongly pulled in then by the black hole. Okay. So to understand what's going on with these systems, you have to think seriously about what actually causes condensation. There's something I've come to call the precipitation hypothesis. And the more I dig around in literature, the more I see people putting forward elements of it. I'm going to give a shout out to Pratik and his collaborators, Mike McCourt, Ellie Clutter, and Ian Parrish, for a couple of papers that really kind of energize the field of brightest cluster galaxies to take the idea of precipitation very seriously. And what do I mean by that? If you just had a hot medium and the black hole is accreting a hot medium, what limits the accretion rate is the entropy of that hot medium. As it tries to compress into the black hole, pressure pushes back. And if you do a classic Bondi problem where it's an isentropic flow, you find that you can't really get enough accretion in these big systems to supply the energy needed to balance the gas around it. In order to get a higher accretion rate, the most straightforward thing to do is to get something else to condense. Okay. If you make the gas into a multi-phase medium, the effective Bondi accretion rate for the cold gas is orders of magnitude higher. And what that suggests is if there's a phase transition where you're going from a single phase medium to a multi-phase medium, there's a possibility that the black hole the black hole's energy output can go up enormously. If that's the way things are, then a system like this will tend to be hung up at the edge of that phase transition. It's like many other kinds of phase transitions. If there's a medium that doesn't have much feedback going on, that medium will cool. If there's a phase transition where you start making cold clouds that can rain down into the black hole and fire up the black hole with a large outburst of energy, that's going to put energy back in, which will tend to diminish the condensation. And so if this transition is abrupt, then these systems should naturally hang up in the marginal state. where there's some condensation happening, but if there's too much, the black hole will push the system back to a longer cooling time where less precipitation will happen. Okay? And so this is a very deep principle that what I'm going to try and make the case for is it may be operating not just in brightest cluster galaxies, but all the way down to the Milky Way and even perhaps to lower mass systems. So why would this transition be sharp? The question of whether a gas blob condenses, it's not yet. So in the simulator in our heads, if we're being naive, it's very easy to imagine if a gas just is cooling that it should sprout a bunch of cold clouds, like naturally. However, it's not necessarily as straightforward as that. If you have a small density perturbation, or really more to be able to say a small entropy perturbation, it can cool on a time scale, T-cool, but it is also negatively buoyant, and it will descend on a time scale that's similar to the free fall time. Okay, and the real question you need to ask to understand whether this turns into a condensate is that this density contrast increasing as it descends, because usually these things are stratified. You'll be going down to higher density regions. A paper I really like is something Pratik worked on with Max Gaspari. And Max Gaspari has a whole string of papers describing what he names cold accretion. This one in 2012 was putting in a bipolar jet mechanism that was fueled by cold condensates. And when you put that into the system, they found this system naturally self-regulates at a minimum cooling time to freefall time ratio of between 10 and 20, and 10 is a floor which is rarely penetrated by the system. So it starts, there's some cold clouds made, they feel the AGN bursts, it puts energy out here, the system ends up here, it stops condensing, then it kind of fluctuates, okay? But it stays much of the time in this range between 10 and 20. And there has since been many simulation realizations by a number of different groups showing this is a very generic outcome. Now, I'll talk. So what's so special about 10, and why is it so hard to condense? If you have a medium now in which the T cooling time is significantly greater than the free fall time, the problem with getting the gas to condense is if there's an entropy gradient. So if you have higher entropy gas here, lower entropy gas down there, you have a blob that's now cooling and descending. If the cooling time is long compared to the free fall time, it will descend to a layer of equivalent entropy and then go past it, and all of a sudden now it's a high entropy blob compared to the surroundings as contrast. And so that blob will start oscillating. And in fact, in the classic thermal instability analysis, that the thermal pumping actually causes those oscillations to increase in amplitude. And they will increase until essentially the drag against the surrounding medium resists that kind of bobbing. And so when it reaches that point, the thermal instability will saturate at an amplitude that depends on this ratio. And so in this case, if T core over T free fall is large and there's an entropy gradient, you get damped oscillations, you don't get condensation. Okay. This actually suppresses condensation. And the first paper I know of that talked about this is actually 1980. And it's a very general physical result that was not forgotten by old people working on cooling flows, but its significance is underappreciated, I think, by legions of cosmological simulators. However, if you have gas that has no entropy gradient, then condensation, there's no buoyant barrier. As you descend, you continue to lose entropy here, the surrounding medium. You're not going to encounter gas of similar entropy, so there's no barrier to condensation there. So in addition to this cooling time to free fall time ratio, another thing that matters is what's the ambient entropy gradient that you're in. Okay, that's going to help determine whether the gas condenses. What's another factor? There's also the the kind of condensation that can be induced by an outflow. And so this simulation is by Yuan Li, as part of a thesis, Lee and Brian, 2014. And there are other people who have worked on this, including Deborah. And so in this simulation, it starts with a homogeneous medium. It's all hot, temperature a few times 10 to 7 degrees. It's essentially a cluster environment without multi-phase gas. There's a black hole algorithm sitting at the center. And it's kind of an algorithm where if gas accretes onto the black hole, it sends out a bipolar outflow. And I'll show you what happens. So at first, single phase, you let it cool, and jets fire up, and you get multi-phase gas along the jet axis. How'd that get there? It is not gas that cooled out locally. The cooling time's too long for it to cool out locally. When the jet starts blowing out, the hot gas rising tends to entrain the volume filling low entropy gas and lifts it up. The effect is a little like a thunderstorm. As this low entropy gas rises, there's some adiabatic cooling, but then rate of cooling takes over. So it's like in a thunderstorm, hot humid air rises until it hits a dew point and it condenses and then raindrops fall back down. And I'll let this thing go a little further. Eventually this gas falls back down in the simulation. And so what's happened here? You had gas that originally had an entropy gradient, and so condensation is inhibited. But if you then take low entropy gas and lift it out, you have not changed its cooling time. Okay, at these temperatures, it's going down in temperature, down in density, but the cooling time has not changed much. And you reach a point where the low entropy gas you've lifted up, you might be in a layer where the cooling time to free fall time ratio is 10 or 20. But if you ask, what's the cooling time ratio of this gas blob to its surroundings, it's more like unity. Okay, it's no longer stabilized by buoyancy and it can condense. That was a simulation. These are actual UV photographs of brightest cluster galaxies. The scale bar is 30 kiloparsecs, and you can see there's star formation on very large scales, not happening in disks. In fact, it's often, or at least in many cases, aligned with the jet axis. And so people were puzzling over, whether these were, where did this gas come from? Was it donated by a merger? Was it condensing straight out of the intercluster medium, then falling in? But I think the emerging story, I think it's an emerging consensus, is that this stuff actually came from the galaxy. It was lifted up by the aging activity and condensed out here. And of course, if you made stars, the gas out at many kiloparsecs from the center has to be molecular when it gets out there. Over long periods of time, in order for these systems to continue in this state, you have to get some of the gas from condensing the hot medium. And it could probably also seeded by stellar mass loss in the central galaxy. A number of us, for the last 5 years, have been trying to get to the bottom of what's so special about this ratio, cooling time or free fall time of roughly 10. And in a minute, when I get to the observational section, you will see why I would obsess about what's so special about T core Q free fall equals 10. Jess said she wrote a paper that was too long in 2016. I wrote one that was too long in 2017, trying to get to the bottom of this issue. And this figure wasn't in the paper, but it helped illustrate one of the ideas. So when you see uplift, you can ask the question, what does it take for uplift to induce cooling? Well, these are simple ballistic trajectories, the isothermal potential. And you ask the question, if I launch something up at a certain multiple or fraction of the circular velocity, how long does it take to come back down? And I can compare that time to the cooling time, because as I lift the stuff up, the cooling time is not changing, but the free fall time is. Okay? So if I launch something up at, say, the circular velocity, it falls back down at about 2.5 times the free fall time. And so if the cooling time, the free fall time ratio here was 2.5, it would cool before it comes back down. Or if I launch it up at 1.5 times circular velocity, it'll come back down between 5 and 6. So if the cooling time free fall time ratio was with 6 here, it might cool before it comes back down. There's also the possibility as it falls, it encounters some resistance from drag that needs to reach a terminal velocity. So maybe stuff here that has a cooling time to free fall time ratio of 8, if you launch it up, it may cool before it comes back down. So drag can lengthen the time of flight. It's also the case that if I have some turbulence in this gas, the random momentum impulses that hit this blob from the surrounding medium can also inhibit the descent. And you might not need such a large uplift velocity to get the gas to condense, as long as turbulence is inhibiting the buoyant suppression of condensation, the present temperature gradient. I wrote another paper about this that might be also too long, but you can go see it on the archive, about how turbulence may also help in this happen. Maybe a more simple way of thinking about it is asking what's now the relationship between this cooling time to free fall time ratio in the ambient medium at the base of this uplifted flow, and comparing to the uplift velocity. I think, I don't know, critique, has anybody ever said to you, I get how the cooling time to free fall time ratio equals 1 leads to condensation, but 10, I have no idea where that comes from, and I don't believe you for that reason. Have they said that to you? I'm not criticizing you. I hear the same thing. Right. Well, anyway, I classified that statement in the role of irrational resistance. I'll tell you why. The cooling time to free fall time ratio less than 1 has to be what you need for condensation is true if the medium is completely static. Okay. But if you just ask, if I am stirring it and creating velocity dispersions that are some, modest fraction of the real velocity, I'm easily going to produce additional fuel. Okay. So if you have a cooling time to free fall time ratio that's, a small multiple of 1, any kind of stirring of the gas is going to induce additional condensation. So if you fire up your AGN and start stirring the gas, you're just going to make more fuel if you're down in this range. Only when you raise it to an order of magnitude higher do the stirring velocities needed to achieve condensation get significantly high. Okay. So the color coding is, in this range, this is so volatile that if you start stirring the system, you're just going to make more fuel. Okay, that's not going to self-regulate. If you raise the cooling time to free fall time ratio very high, no amount of disturbance is going to condense. And so there's a sweet spot around 10 where if feedback can raise the ratio of cooling time to free fall time in that gas to in this range, then it's going to be roughly in balance. Okay. So, to kind of summarize this, something that people who wonder about multi-phase mediums should take more seriously is if you had an entropy stratified medium with a large cooling time to free fall time ratio, condensation is going to be inhibited. You just don't get multi-phase medium all the time. Okay. So if you want to get multi-phase gas, one of the following things needs to happen. Well, you could just lower the time free fall time ratio. Right? You could also flatten or invert the entropy gradient. In fact, I think this is happening in a lot of cosmological simulations that do what they call AGN feedback, where they just do a heat dump in the center. Because when you do a heat dump in the center, you invert the entropy gradient, and you're actually promoting condensation. And those cosmological simulations find they have to put enormous amounts of AGN energy in just to stop the condensation. But I think there's something fundamental about the physics that is not right about that feedback. You could also do a bulk uplift of low entropy gas, which is really like a local inversion of the entropy gradient. Put some up here. So there you've removed the barrier. Or you can stir it. So there are some ranges of parameter space where if there's enough turbulent stirring, you're going to inhibit the buoyancy that is kind of suppressing condensation. All right. So if you're going to have feedback that either that regulates the cooling of the certain electric medium, it's going to have to be a mechanism that is managing these different things that influence the condensation process. So what about evidence? Why am I bothering talking about this? Here's two of my friends. This is, you've seen this before, this is the Central Galaxy Coma cluster. So at least half of central cluster galaxies don't have any of this stuff going on, and they're just happily single phase. And you kind of inspired by the papers that Pratik was writing, we went back and said, okay, if we just graph the cooling time profile as a function of radius and separate the groups into galaxies with multi-phase gas and galaxies with no multi-phase gas, you get this very distinct dichotomy in the cooling time profiles. And also, if you draw on some guides to the eye, this is the kind of cooling time profile you would expect with pure cosmological structure formation at large radii. Both classes of systems follow that line. But then you also draw on another line that says, where would the cooling time be 10 times the free fall time? It's right along here. And this group of things that have multi-phase gas, the lower envelope tracks right along the 10 line. And so,
It's the same distinction as between Pluto clusters and non-Pluto clusters?
yes. Well, in one sense, you can say the distinction between those classes depends on what metric you're choosing, and there are zillions of them in the literature. If your metric is, does it have multi-phase gas or not, well, then it's like 1 to 1. But it is true that these are the cool core clusters, and those are the non-cool core clusters. You could also see if your metric is the central cooling time less than or greater than a gigayear, you would get the same kind of dichotomy. Or, central entropy value 30 keV centimeters squared, you get the same kind of dichotomy.
But it's a good correlation between the
Yes, sir. It's a good correlation. It's just people, way too many of them in the literature. Okay. Here you go. The question is now transitioning to how much of this can be just transferred to lower mass systems. Again, another paper from Pratik in 2012. These are model density profiles where first you say, what would the cosmological density profile be, electron density profile be, as a fraction of, or as a function of R over R200, and this is fairly self-similar for many different systems if there's no cooling or feedback. But then you can say, all right, well, if you say there's a limit where T equal to free fall equals 10, well, that limit is more severe as you go down in halo net. Okay, and so this profile tends to be like R to the minus 2. These tend to be like R to the minus 1. And so they'll eventually intersect the cosmological limit. But another way of looking at this is that the density, central gas density tends to be more and more strongly suppressed by this limit as you go down in halo mass. And so in an effort to try to kind of see how far this idea can be pushed, you can't get really nice cooling time profiles down to galaxies that are Milky Way scale, but you can do this calculation where you say, if this limit is an important thing, you can do some algebra to make it an upper limit on density, electron density. Then you can integrate electron density over radius, or times a cooling function, to get the luminosity limit from within a given radius as a function of radius and as a function of temperature. So if you just assume the gas is isothermal and the potential is isothermal, you get out a quantity that's the limiting value of extra luminosity from a given radius as a function of temperature and radius and sigma. Okay, this is a complicated function of temperature, and you can plot it up. Okay, if you take the galaxy clusters and put them on there, these tracks are just saying as I increase the radius in which I'm measuring luminosity, I'm going to measure more and more luminosity, and so luminosity is going to rise, but so is this limiting thing. And so you can see these tracks for the multi-phase system start at very close to the limit and then go over the cosmological regime at large radii, and the single-phase systems don't enter this zone where T equals T free falls between 10 and 20. You can also put groups on there at radius of R500. You can put on entropy profiles from the sample kind of grouted out. You can look at very good observations of individual elliptic galaxies by Norbert Werner. You get these tracks going out in radius. And then, if you really get greedy, you can get data on the massive and Atlas 3D galaxies and put them on there. And there they are. And then you can take the Miller and Bregman model for X-ray emission around the Milky Way, and it's there. Okay. So over almost 7 orders of magnitude in X-ray luminosity, this limit seems to be very profound. Okay. There's things that it doesn't get violated. And not only that, but in the massive and Atlas 3D galaxy sets, you have information on whether it has phase gas, either in the form of nebular emission or CO emission. And the closer you get to this precipitation limit, the more likely it is that you'll have multi-phase gas in these early type galaxies.
How does this hot gas profile compare to the one that Jess had been using?
I will get to that. Okay. Now, that was as a function of radius. Here it's just what's luminosity from within R500. And given the diagram for Tika I showed earlier, as you go down in system mass, this precipitation limit suppresses the density out to larger and larger radii. And that tends to suppress the luminosity temperature relation. You can put on galaxy clusters, individual objects, and fit the luminosity temperature relation. It goes down like this. These squares are from a stacking analysis that was done by Anderson et al., where they took Rosenthal sky survey massive galaxies, binned them by stellar mass, hundreds of thousands, and then measured how much X-ray flux was within R500. And in the cluster regime, of course, it tracks, but it maintains the same slope as clusters do, all the way down to almost Milky Way masses. So when you're talking about ambient medium, in any average sense, the hot gas around massive galaxies is a lot like clusters with this extra suppression from this limit. And the Milky Way, out to 100 kiloparsecs, lies right in the galaxy cluster LT relation. One of the things you do when you come to India is you find out about papers that you should have read. This is one that Beeman Nath is on. Where they also did a stack analysis jointly fitting X-ray and SZ effect stacks. And here is their best model for a power law hot CGM. You'll notice the column density of the ambient medium does not vary very much with impact parameter, which is kind of like the 06. All of this is essentially a high-strike hot halo model. It's just the density profile is shallower. If you ask for these kinds of systems, where's T equal T free fall equals 10, that would be the precipitation limit. So the precipitation limited systems seem to be a very good match to the stacked ambient medium measurements that people are getting from X-ray and SZ effect. Okay. Right. How much time do I have? 1 minute. Okay. Yeah, all right. Okay, I'll try to go from. Okay, in a few minutes, we're going to hear talk about galaxies that are wind regulated, where here comes the cosmic accretion. Most of it gets into the galaxy. Then you have to blow it out with the wind, and it goes off, and maybe there's some recycling. So this is kind of the standard way people think about feedback regulation of galaxies. What I want to point out is what I've been talking about is an entirely complementary form of regulation, where if instead of most of the gas getting in the galaxy, most of the gas goes into the CGM, you don't need quite as dramatic a wind to keep the star formation at an appropriate level. But what happens then is the gas goes in the CGM, and there's a possibility that it could precipitate back down. If there's feedback, it tends to pump up the CGM, so it expands. It doesn't go off to infinity. And the point I wanted to make about this is here, if you're needing to manipulate the mass loading factor to get the right relationship between baryon, stellar stars, and halo mass, it's an internal mechanism to the galaxy. But this mechanism is really a feature of the circular medium. And massive systems at late times, this appears to be the dominant regulation mechanism. The last thing I want to do is just go back to the Milky Way and show a couple more slides. One is, again, from this paper by Singh, and Silk, where they also compared their model to the Milky Way. And there's a bunch of lines here that are useful to the conversation we were having at the end of last talk, where this is their best model for the Milky Way, the blue. These data points are estimates of the mean density of the ambient medium around the Milky Way from stripping of dwarf galaxies, and also the Magellanic Street. The dotted line here is the Miller and Bregman X-ray analysis. And they're all in pretty good agreement about what the ambient medium density should be. I will point out in passing, I mentioned this to Jess Durham last time. In the nebula in cluster galaxies, central cluster galaxies, those filaments, those 10⁴ filaments, are underdense compared to what you'd expect from pressure equilibrium. That's thought to be because of magnetic support. So again, I don't know if it's the same thing for the same reason, but we also find they're underdense, or presumably underpressured if you're just relying on thermal pressure. And that's the T-core or T410 limit. Okay.
On this plot, that green way down there is like the Mallory-Bullock hydrostatic.
It was a particular model that they had in their paper. They looked at a power law model for the
it looks
distribution,
lower.
And this is not the only hydrogenic level model you can cook on.
Okay.
It's the one they used in the paper. This one is better. I don't know. It wasn't inspired by Mahler.
I thought that came from a semi-cosmological simulation where they prescribed an infall rate. The Fielding et al.
Oh, yeah, there's the Fielding. Also, this is, the Fielding et al. Is where they...
Oh, sorry. Looked at the wrong one.
Yeah, that one. That's a self-regulated, supernova-regulated CGM, which tends to tune itself to T-core P3 at all time. Last slide before this one. I wanted to make an introductory spectroscopy, partly because I'd love to see the links mission. This is a unique and uniquely powerful line of sight. It's a line of sight in Parks 2155, a BLAC object that was used to calibrate the XMM. They have 3 million seconds of calibration data on this power law source. And along that line of sight, they're able to measure the Milky Way's absorption in options 8, option 7, option 5, option 4, along with a bunch of other ones. And so this is a line of sight where you have a complete set of ionization states. And perhaps it's surprising, but the equivalent widths in option 4 and 5 are quite substantial. There's a lot of gas there in these phases that really haven't been seen before. And if you take the analysis at face value, you can ask, I have an option 4 to 6 ratio, option 6 to much better. There's an option 4 to 5 ratio. If you're trying to make these ratios with the superposition of collision ionization equilibrium models, you will find yourself on this line. If you ask about isobaric cooling, you just take gas cooling down through high temperatures to low temperatures. In this regime, the peak of the cooling curve, you tend to cool faster than you recombine. You go out of ionization between somewhat. And if you had solar metallicities, you would be on this line. If you have a tense solar, you are cooling even slower and you get even more out of ionization equilibrium. Their best data point indicates that what you're seeing here is gas that's cooling and going somewhat out of ionization equilibrium, indicating that your transitions in looking at halo in almost one line of sight will tend to be very dynamic, phase-changing kind of system. So option 6 can only be there if it's transient. All right. Yes, no one recorded with observations, and this is what I tried to do.
Okay, questions? Yes.
Thanks for this very exciting talk. Many questions, but would like to select the one on the Milky Way here. So you have this interesting limit, which sounds amazing, that the cooling time is about 10 times the default time. And I guess that limits the galaxies that can have about 8 or 2 power Milky Way size mass. So if they are lower metric content,
I would argue the feedback has to push the gas to a lower density. And the jury's out as to whether it's there. But if you take this model at face value, let's say if you go down to sub-Milky Way, it has even less dense and medium. So that could be. That's right. To say the same thing, you have to inflate the circuit black medium even more.
But then you have to go from that if you get temperature is also needs to be low.
Yes.
Not getting in hyperspectral equilibrium.
Well, you still can. I can break down the model with it.
Yes, well.
So, another question is, I mean, on the basis of energetics, the feedback agent has to be the central supermassive black hole that we call like halos, but as you go down in the halo mass, principle couldn't be subatoms. So, what would you have to say about that?
Here's what I have to say. I'm back to this one. This fielding it out simulation, what they did is they was idealized simulation where they had a kind of a circular black medium inflow, which you can cosmic accretion coming in smoothly. And at the center, they have a galaxy that is just producing supernova feedback. And that system is very close. It's tuning itself quite close to this accretion. So there, the black hole was not necessary to achieve this circumstance.
So where did the transition from?
Well, the way I look at it is, I'm a little agnostic about that. When I'm thinking about the physics, it is, if the circular medium gets too dense, it will make cold gas. Whatever gets ignited by cold gas will happen. If it can supply enough energy, one mechanism to supply enough energy, we're good. If supernova ever fail, the black hole would take up from there. And in order to answer, which thing is more important, you need to know how efficient this supernova energy is coming.
Okay, question in the back?
I just want to comment about the plot which you showed from Gaspari's paper for minimum gigawatt TC form. If you go back to that plot, you will see that after 2 gigayear time scale, the minimum gigawatt TC form sort of fluctuates around 20 rather than 10. If you look at their simulations, what you will find is after 2 gigayear, they do not have any multi-phase gas as such. The cold gas is limited in the central 5 kpc, so essentially it's not, they have essentially overheated the entire system after 2 gigayear.
So this is the first simulation of its kind. And what people have found is sometimes these systems tend to develop long-lasting disks because of angular random stochastically generated.
They do have this, but after 2 gigayear, they do not have any long filaments, or their cold gas has got saturated in the disk. They have just overheated their system. The entropy, after about 5 kiloparsec, is very high, and essentially they have just dumped so much energy that you do not have any multi-phase gas after that.
There's one. There's a rabbit hole here about the details of implementation. You don't have to go down that today. generically, they tend to rate.
Okay, last question. So
Make predictions about the turbulence, the level of turbulence, medium, this becomes totally different numbers from the cluster, but what would be the predictions of your other system also?
I do make a prediction, and
Have they published?
Eventually
Make
they
a
will.
prediction before the data.
If I persevere, there's a paper on Ash Page, I think in March, where I asked the question, how much turbulence would be necessary to make the critical ratio around 10? As you raise the turbulence higher, you can get condensation of a higher ratio to working freeform, because you're more able to suppress the plants. In that paper, I showed that the amount of turbulence necessary to get T4 Q3 flow equals 10 as your condensation point is turbulence is about half the stellar velocity dispersion, which is what you see in Perseus. And it is what you see in the magnesium tube lines from Perseus. And increasingly, as people start to estimate the amount of turbulence, the Plutonian observations you get turbulence from magnets. But there are several other well-observed galaxy clusters where you can get turbulence estimates from surface radius fluctuations. And they also tend to have turbulence at about this level, half the stellar velocity dispersion. The model predicts that if you have something that's too quiescent, no turbulence, you have to go down to lower range turbulence. Curiously, the most quiescent of these systems where people can get turbulence from surface space fluctuations is about 2029, which you would probably recognize as the greatest celestial galaxy that's a short central cooling time and very little So there's a few predictions in there about that correlation, but
You go to predict, so you really publish it.
let's
What the data will show you a chart.
yes. It will be published as soon as the referee lets them.
Okay, so we need to move on. Let's thank Mark again.